Okay, good morning, algebra. We are going to continue looking at just how things change, and we're again not going to be too crazy involved in like specifics about new learning. We're just going to be noticing that we're dealing with a different type of change in this unit. So not linear, not exponential, we're looking at different types of change. So the warm-up is 2.1. How does each expression represent the number of small squares in the figure? So take some time and look at each of these expressions. How does this represent this whole shape? We'll look at it in a bunch of different ways. My drawing's probably going to be messy, so I'm very sorry about that. But really take time, pause it, and see how does each one of these reflect this? How does this reflect that? Okay, so the first thing I'm going to notice about this shape is I have 1, 2, 3, 4, 5, 6, 7, 8 boxes wide, and I'm 6 tall. But also I have this little cutout over here, which, if you count, would be 2 by 3. So I think that's where this expression right here comes from. 6 by 8 is the whole minus the part that's missing. And our next one is similar but slightly different, because this one looks at two pieces being added together. A 4 by 8 being added to a 2 by 5. So if I look, this right here is 4 tall and 8 wide. So that's my 4 by 8. And then 2 by 5, this right here is 2 tall, and it is 5 wide. So it's the bottom being added to the top. So 8 by 4 plus 2 by 5. This one here, all these different things being added together, 8, 8, 8, 8, 5, and 5. Well, if I look at my rows, I have a row of 8, a row of 8, a row of 8, and a row of 8. I have a row of 5 and a row of 5. So I have 4 rows of 8 and 2 rows of 5. So here we're just adding the rows. And this one here, we have a 5 by 6 plus a 3 by 4. Let's see, that looks kind of like expression B, but 5 by 6 is really like that left piece plus 3 by 4, that's my right piece. So that's the 4 ways this is being expressed. So we're gonna look at patterns in all different ways. Please pause it when necessary, because you might notice the pattern differently than I do. And the goal is to make sure that all of our noticings still lead to the same conclusion. So don't be afraid to notice things differently. All right. So we're gonna look at 2 different patterns of dots. And we're gonna notice how are the number of dots changing in each pattern. So how is the pattern being changed? And how would you find the number of dots in the 5th step in each pattern? So take a minute and pause it, and then I'm going to show you what I'm going to highlight as what I see as being added on to each image. For pattern 1, step 0 looks like just 1 dot. So what I'm seeing as step 2 is I'm seeing it as, or step 1, I'm seeing that it added a column of 2 to the right. And then step 2 again, it's adding another column of 2. And another column of 2 is being added every time. But you might have seen it differently from me. So another way to look at it is you could say, all right, well, here's this one. And it looks like, oh, they added 1 above and 1 to the left. And then here again, oh, they added 1 above and 1 to the left. And then, oh, over here, starting with my original 5, they added 1 to the left and 1 above. So you might see it in all those different ways, but I'm going to treat this the rest of the way like I saw the highlighting. All right. So I'm going to say it's adding 2 dots to the right each time. So how would I find the number of dots in the 5th step in each pattern? Well, So I've noticed that in step 1, there's 1 column of dots. In step 2, there's 2 columns of dots. So in step 3, there's 3 columns of dots. So in step 5, there will be 5 columns. The shadow's bad. 5 columns of 2, much better, and 1 on the left. So it's going to be 5 for this 5th step times 2 plus 1. So it'd be 11. All right. So the same thing for down below. Pattern 2. Okay, step 0's got nothing. Okay. So really in step 1, what was added was 1 dot. And then in step 2, let's see, it looks like it added 2 above and 1 to the right. And then in step 3, I'm seeing it looks like it adds a row above and a column to the right again. So this one's a bit harder to come up with. Like, what rule do we think we can come up with for that one? So there's a couple different things you might think about for this one. One thing I'm noticing is it looks like it's adding, it's adding in squares is what I see. So step 1 is 1 by 1. And step 2 is 2 by 2. And step 3 is 3 by 3. So you might be thinking step 5 is 5 by 5. Or another way you might be thinking is like, well, to go from step 1 to step 2, I took 1 and I added 1 above and added 2 to the right. And to go from step 2 to step 3, I had 4 and I added 3 above. I'm sorry. Yeah, 3 above. No, 1 above. I'm going to try to stay consistent. 2 above and 3 to the right. So really, I'm taking my original amount, which was my 1 by 1, and adding that same amount, or adding the step number that I'm on, and then adding 1 more than that. So whatever, I like this first way better. So you might be seeing that step 5 would be 5 times 5, or would be 25 dots. All right, you probably saw it more like this. The way I was doing it down here is a little bit stranger, but we'll see why that works hopefully later. So on the back, we're completing tables with a number of dots in each pattern, and the goal is to come up with a rule for n. Like if I have an arbitrary x, like what's happening down there? Take a few minutes, fill in. We already know that pattern 2 started with 0 and 0, and then it had 1, 4, and 9. And this one, for pattern 1, was 1, 3, 5. So fill in the rest of those and try to come up with that rule for that bottom part. So hopefully you came up with these numbers, unless you're like me and you misread that this was actually 10, not 6. I accidentally wrote 13 right here, and then I have to change it to 21 because this is step 10, not step 6. And I noticed that this is linear growth right here. For the left column, it's linear, going up by the same amount each time. We're adding 2 dots every time. So I found my slope of 2, because it's adding 2 every time. And I said, all right, well, if I'm adding it 5 times, then I have to add 2 times 5, so I get 21. And I also sketched it out over here, like, okay, stage 0 is here, stage 1 is here, stage 2 is here, adding 2 every time. Stage 10 has 21. So there's another way to figure that out for you. And in pattern 2, the number of dots we have is n squared. And you could have probably come up with something very similar to that, by thinking about it a little bit differently. So I want to see if anyone came up with a different method for it. So here's one more way to think about that rule. And if you don't like this way, that's fine. You can ignore me, but it's actually pretty cool how it actually ends up working. So you can think about this as well, growing by, let's see, so if I start at step 2, for example, step 2 is really 4, which is really that original 1, plus the 1 above it, and the 2 to the right. And this next one, step 3, is stage 2, which is the 4, which is the original, plus the 2 above, and the 3 to the right. So all of these numbers have a special corresponds to the step number. The original one, the original number, is the n minus 1 squared, because the previous number squared. Because in step 3, the original was step 2, which was 2 squared, so that was 4. And then we added in 2 above it from that previous step. So we added in the previous step, which is n minus 1, which is the top. And then we added in our 3 to the right, which was our original n number. And we don't have the math to prove this yet, but this is all actually the same exact thing as just saying n squared. It all counts out and turns into this, which is super cool and would be a really cool assignment to do like much later in the unit. If you didn't think about it like that, that's fine. You can all continue paying attention now. But if you did come up with that, props. If you understood it, props. Let's keep working. So anyway, here's our rules. So we're gonna plot the number of points at each step number. So this should be easy. Go ahead and try that. And question 4, we'll talk about that maybe briefly. We'll make the graph. So here's our graphs coming from the data above. And the graph 1 is linear, constant growth. It should be a straight line. That's why it looks that way. And number 2, we notice it's not linear, because it's not a straight line, but also it's not exponential, even though it is curved. Because remember, exponential graphs, they do not touch 0. Remember that. If you take something and you half its value every day, it never quite hits 0, remember? So exponential graphs never hit 0, which this one starts at 0, so it's not exponential. All right, so again, we gotta find a new kind of growth for this. And that's also noticed because that's n squared. Exponential would have been 2 to the n power. All right, so let's keep moving. We're doing great. We're almost done. So we got one more pattern to look at. So let's think about this one. Is the number of squares growing linearly? So try to figure out how is the number of squares growing and try to complete the table below it. All right. Okay, so this is the first way I thought about it. I was like, well, I got 3 lines, or I'm sorry, 3 boxes. And then I added 2 tall and added 1 to the right. And then, okay, next time I'm adding 3 up and I'm adding this and then this over here. So I'm adding 1 over here, but then I'm making each row 1 taller, 1 wider. So I'm adding 3, I'm adding 5, and I'm adding 7. And I don't have a really good way to write a rule for this yet. So we're just keep trying to think about that, but I'm going to also show you a different way to think about this. Okay, so I thought about this one a different way. So this time I thought about it like, well, I noticed it's kind of like a box with 2 little tails on the side. And that box in the middle is the original step number squared. So it's 2 by 2, 1 by 1. And over here I got a 3 by 3. And then I'm consistently that I always have those 2 tails on the right. And here I got a 4 by 4. So I think for my rule, what I'm going to write down here for n is n squared plus 2. All right, and I think that's going to suffice. And then I'm going to fill the rest of my table in. So, all right, 5n squared. So I'd have a 5 by 5, which is 25, plus 2 is 27. 10 by 10 is 100, plus 2 is 102. 12 squared, 144, plus 2 is 146. All right, is the number of squares going up exponentially? No. And I'd say there's no growth factor. And I can prove that with my table very, very easily, because 6 divided by 3 is 2, which is t-rif, but 11 divided by 6 is not 2. And neither is any other number divided by its previous. None of them are the same growth factor. There's no common growth factor. Okay, last one's real tricky. So we're just gonna walk through this one. Han wrote this, and I didn't put one of your names in for it because no one, I don't know how this even came up. Like, I have to figure this out myself. But basically, how come he's correct here? He said this, 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 and this. He said n quantity n plus 2 minus 2 quantity n minus 1 is a rule for that at step n. So let's just think about where in the world this came from. So I think it'll be easier to tell if we look at one of the later steps. Like let's look at step 4. I guess I'll just redraw that again down here. Magic. I didn't want to put you through the struggle of watching me try to draw this again. So this is step 4. So let's think about what all these things are. So if this is step 4, that means that n is 4. And n plus 2 would be 6. So where do we see 4 by 6 here? Well, think back to our warm-up. The 4 by 6 is kind of like the entire thing, right? That 4 by 6 is the whole thing. It's 4 tall and 6 wide. And then what do we take away from that? Well, we take away 2 groups of something. And what the heck is n minus 1? Well, n minus 1 here would be 3 because n is 4. And oh, here's the 2 3s we're taking away. So that's really where this whole thing comes from. It was actually pretty cool where this comes from. I don't expect you guys to come up with that, but if you did, you're amazing, because I didn't. And we could even use our distributive property to prove that this turns into that, unless I'm wrong, which is going to be very awkward. So let's try it. We did number 2, actually. We labeled the picture. That's very good. So let's distribute now. Let's do n, quantity n plus 2, minus 2, and minus 1. So n times n is n squared. N times 2 is 2n. Negative 2 times n is negative 2n. Negative 2 times negative 1 is plus 2. And by golly, those cancel. So we get n squared plus 2. Pretty nuts, isn't it? All right, so there's that. Good lesson today. Just fill in your assignment for today and hope it goes well. Email questions.